First example, of Marianne's closest girlfriends, 5 are married and 5 are single. If Marianne randomly chooses 3 of her closest girlfriends to be bridesmaids at her wedding, what is the probability that all 3 will be single? Marianne is getting married. Somehow I always thought that Ginger would go first. And of course, to be fair, Marianne is going to choose her 3 bridesmaids randomly. I guess she writes the names of each of her 10 closest friends on a sheet of paper, folds it in half, puts them all in a hat, and then she selects 3 randomly. And it could happen. For the sake of our example, we'll suppose that that's exactly the way that it happens. And E is the event. E is the event. All 3 bridesmaids are single. That's the event. And we want the probability of that event. Probability of E occurring. And before we do this formula, let's remember that Marianne is randomly choosing these 3 bridesmaids. So every bridesmaid, each of the 10 bridesmaids, is equally likely to be chosen. And therefore, we can use the formula, number of outcomes resulting in E over the total number of outcomes. And what is E again? We're selecting 3 bridesmaids. And we want all of those 3 to come from the set of 5 single bridesmaids. Does order of selection matter? Does it matter which one is selected first? It doesn't, does it? The girlfriends are either chosen to be a bridesmaid or they're not. So order of selection is irrelevant. This is a combination. And from the set of 5 single best friends, we want the number of combinations of 3 single best friends that can be selected from the set of 5 best friends. And what about the total number of outcomes? Again, any outcome is going to result from these bridesmaids, 3 of them, being randomly selected. The number of ways that this can happen, it's a combination of 3 bridesmaids selected from a set of 10 bridesmaids. And we'll probably choose to do this on our calculator. We'll enter the first number, 5, and hit the probability button. And then we'll hit right arrow until NCR is underlined. And when NCR is underlined, we'll hit enter. And we'll enter this, and we'll type the second number, 3, and hit enter again. And if we do this, I think we'll get 10. Down here, we'll enter the first number, 10. We'll hit the probability button. And again, we'll hit the right arrow to move the underscore under the NCR. And when the underscore is under the 10CR, We'll hit enter. And we'll type in the second number, 3, and we'll hit enter again. And when we do, I strongly suspect that we'll get 120. And that means that our probability will be 1/12. Here's another good one. 20 young adults are selected at random. Of the 20, only 5 have had the measles. If 3 people from the 20 are selected at random, compute the probability that none have had the measles. Okay. Is the event that of the 3 selected, none have had the measles. Now let's look at our information here. Of the 20 people, 5 have had the measles. So what does that mean? That means that 20 minus 5 have not. Fifteen of the 20 have not had the measles. We want to compute the probability that E occurs, that of the 3 selected, none have had the measles. We're going to choose 3. Does it matter what order they've been selected in? It really doesn't. The only thing that matters is they haven't had the measles. If we select 3 people, either they've had the measles or they haven't. And we're looking for 3 people who haven't. So we're going to select 3 people who have not had the measles out of a set of 15 who have not had the measles. And you know what? I'm jumping the gun here. Before I do this, let me use that basic rule of probability again. The probability that E occurs given that all outcomes are equally likely, number of outcomes resulting in E over total number of outcomes. There we go. Now we're getting started off on the right foot. The number of outcomes resulting in E. We choose 3 people out of 15 who do not have the measles or who have not had the measles. So of those 15 people who have not had the measles, we want to know the different number of combinations of 3 people that we can choose, because order doesn't matter. So of the 15 who have not had the measles, we want to know the number of different combinations that 3 of them can be selected. And then the total number of outcomes from a group of 20 people, we want to know the number of different ways or combinations that we can select 3. Holy moly. I should know what this is. I wrote it down. On our calculator, this is a combination. We'll type in the first number, 15. Then we'll hit the probability key. And we'll hit the right arrow to move the underscore under NCR. And when the underscore is under NCR, we'll hit enter. We'll enter the second number, C, the second number, 3, and we'll hit enter again. And that should give us 455. We'll do the same thing with selecting a combination of 3 people from a set of 20. We'll type in the first number, 20. We'll hit the probability key. Then we'll hit the right arrow until NCR is underlined. And when it is, we'll hit enter. We'll type the second number, 3, and we'll hit enter again. And this is 1,140, which reduces a little bit. 91 over 228. Probability that E occurs in this case, 91 over 228. Let's take a look at this exercise again and see if I can do it a different way. Same exercise. 20 adults are selected at random. Of the 20, only 5 have the measles, or only 5 have had the measles. 3 people of the 20 are selected at random. Compute the probability that none have had the measles. Our event is that of the 3 selected, none have had the measles. So let me ask you something. Can I do this? Probability that E occurs is 1 minus the probability that E doesn't occur. E is the probability that of the 3 selected, none have had the measles. So I'll say not E is the probability that of the 3 selected, all have had the measles. And so I'll say probability that E occurs is 1 minus the probability of not E occurring. And that's 1 minus number of outcomes resulting in not E over total number of outcomes. Now the bottom we did before. We have 20 people, and And of those 20 people, we're going to select 3. And let's see, what was that? I think, if I'm not mistaken, I think that was 1,140. Okay, the number of outcomes resulting in not E. Okay, let's see now. Not E. There are 15 people that do not have or have not had the measles. 15 have not had the measles. And we want, hang on a second. Okay, forgive me, I was confused for a second. But not E, the way we've defined it, is that of the 3 selected, all 3 have had the measles. Now, in the entire group of 20, only 5 have had the measles. So if we want all 3 of the people that we select to have the measles, we're going to be selecting that group of 3 from the set of 5 that have had the measles. And order of selection isn't important, so this is a combination. And if we compute number of combinations of 3 people selected from a set of 5, oh, you'd think that I would have computed this. I believe that that's 10. Whoops, and forgive me. One minus outcomes resulting in not E over total number of outcomes. So I have 1 minus the number of ways that we can pick 3 people who have had the measles out of a set of 5 people who have had the measles. And there are 20 people total from which we're selecting these 3 people. Okay, that looks better. I had forgotten the 1 minus before. And that leaves me with 10 over 1,140. And that's 1 minus 1 over 114. And that turns out to be 113 over 114. Which is great, but that's not the answer that we got before. Let's see, what did we get before? Ah, my goodness. Let's check. Before we reduced, it was 455 over 1140. Well, that's not what we get here. We don't get 455 over 1140. And if I hadn't reduced here, what would I have gotten? 1130 over 1140. Before we reduce, this is what we get for an answer this time. But when we did it before, we had 455 over 1140. we didn't come out with the same thing that we came out with beforehand. Why is that? I made a mistake in logic. Can we pick it out? Let's examine this closely because this is an easy mistake to make if we're not thinking about things carefully. And the logical mistake that I made was right in here before we actually started crunching any numbers. I thought, okay, the probability of E, that's 1 minus the probability that E does not occur. And this much is right. Here's my mistake. I said that not E is the event that of the 3 selected, all 3 have had the measles. Now, is that really not E? E was of the 3 selected, none have had the measles. From our study in logic, none have had the measles. Now we want to do the negation. What's the negation of some have? I'm sorry, what's the negation of none have had? And it's not all have had. The negation of none have is that some have. Now here, when we did this before, we assumed that the negation of none have had the measles was that all have had the measles. But the negation of none have had the measles is that some have had the measles. So here's our problem right here. I said, aha, if E is the event that none have had the measles, then not E is the event that all have had the measles. That's not right. The negation of none have had the measles is that some have had the measles. And what could that be? Well, at least one. One has had the measles, or 2 has had the measles, or 3 has had the measles. Oh my goodness. So this was the problem. We thought it was going to be easy to negate the event E. E is the event that none have had the measles. And we said, okay, if E is the event that none have had the measles, then not E is the event that all have had the measles. Oops, that was our problem. Big oops. Right here. The negation of none have had the measles is not all have had the measles. The negation of none have had the measles is that some have had the measles. And that means 1 or 2 or 3 had the measles. And that's a fairly complicated probability to compute. But this is a mistake that we could make if we're not careful. If we're computing the probability that none occur, the negation of that event is not the probability that all occur. So we want to watch out for that trap. The way we did the exercise the first time was by far the easiest way. The event not E involves one person could have had the measles, or exactly 2 people could have had the measles, or exactly 3 people could have had the measles, and we'd have to figure out all of those probabilities and add them up. So the way we just did it, it was incorrect the way we did it. And even if we correct things, it's going to be a fairly hairy exercise to compute. But the bottom line again, and the mistake that we made here, E was the event that none had the measles. And naively we said, okay, well that's 1 minus the probability that E doesn't occur. And this is right. The probability that E occurs is 1 minus the probability that E doesn't occur. But our mistake was we said, okay, E is the event that none have the measles, which means that not E is the event that all have the measles. This was the big problem right here. The negation of none is not all. And that's why we did not get the same answer when we ground this out. It's a naive mistake, but if we're not thinking carefully, it's a mistake that we can make even though we know what to look out for. So I'm just highlighting this so that we'll beware. This next exercise has a nice little twist to it. 10 men and 8 women apply for 4 open positions at a bank. If the successful candidates, left out a word here, I think, if the successful candidates are selected at random, what is the probability that 2 men and 2 women are selected? We have 10 men and 8 women, 18 people total, applying for 4 open positions. The successful candidates are selected at random. So every person is equally likely to be selected. What is the probability that 2 men and 2 women are selected? Well, let's see. First of all, notice that the order of selection is irrelevant. It doesn't matter who gets selected first, who gets selected second, who gets selected third, and so forth. The only thing that matters is they get selected. So a person is either selected or they're not selected. The order doesn't matter. So we're talking about combinations here, not permutations, but combinations. Let E1 be the event that 2 men are selected, and let E2 be the event that 2 women are selected. And we'll let N1 be the number of ways that E1 can happen. Now think about this. We want 2 men to be selected, and they're going to be selected from 10 men. The order of selection is irrelevant. So this is going to be a combination of 2 men selected from a set of 10 men. We'll do the same thing with women. We'll let n sub 2 be the number of ways that E2 can occur. Tell you what, let me move this down a little bit. I don't want all of these figures to be packed in so tightly we can't read them. N2 will be the number of ways that E2 can occur. So let's see, with E2 we're selecting 2 women from a set of 8 women. So this will be a combination of 2 women selected from a set of 8 women because the order of selection is irrelevant. Okay, that looks good. Now, what do we want? We want E1 and E2 to happen. We want E1 and E2 to occur. 2 men selected and 2 women selected. So this is really going to be a 2-stage experiment. The first stage, we're going to select 2 men. The second stage, we're going to select 2 women. So the fundamental counting principle applies. And remember what the fundamental counting principle says. If E1 can occur in N1 ways, and E2 can occur in N2 ways, then E1 and E2, how does the rest of this go? E1 and E2 can occur in N1 times N2 ways. That's what the fundamental counting principle says. So this tells us E1 and E2 can occur in N1 times N2 ways. N1 is a set of two elements, a combination of two elements selected from a set of 10 elements, times a set of two, a combination of two elements selected from a set of 8 elements. This is the number of different ways that we can select 2 men and 2 women from a pool of 10 men and 8 women. So E1 and E2 can occur this many ways. Now, remember how to compute the probability of events E1 and E2 occurring. That's going to be the number of outcomes resulting in E1 and E2 divided by what? Right, total number of outcomes. Number of outcomes resulting in E1 and E2, that's this thing. This thing times that thing. And how many outcomes are there total? Well, let's see. We're selecting 4 people. And how many people are we selecting those 4 people from? There were 10 women, there were 10 men and 8 women. So we're selecting 4 people from a group of 18. And selection or order of selection is irrelevant, so this is a combination. We're selecting a combination of 4 people from a set of 18 candidates. Holy moly. To compute this, and let me rewrite it a little bit better. To compute this, we'll type 10, hit the probability button, and then hit the right arrow button until NCR is underlined. And we'll hit enter. And then we'll type in 2 and hit enter again. We'll do the same thing for this. We'll type 8. We'll hit the probability button. We'll hit the right arrow button until NCR is underlined. Then we'll hit enter to select NCR. We'll enter the 2 and we'll hit enter again. And we'll do something similar for this. And this comes out to be 45 times 28 Holy moly, what is this thing? 3060. And that boils down to 7/17 or 0.41176. Here's another good one. 6 cards are selected at random from a deck of 52 cards. What is the probability that 2 clubs, 2 diamonds, 1 heart, and 1 spade are selected? We're selecting 6 cards. What's the probability that we get 2 clubs and 2 diamonds, 1 heart, and 1 spade? Now, does it appear that the order of selection matters? Nope. It just says 2 clubs, 2 diamonds, 1 heart, 1 spade, no particular order. So again, order doesn't matter. We're going to be working with combinations here. Let E1 be the event that we draw 2 clubs. And let N1 be the number of ways that we can draw 2 clubs. E1 is the event that we draw 2 clubs. N1 is the number of ways that that can happen. We want to draw a combination of 2 clubs. And how many clubs are there total in the deck? 13, right? So we're selecting a combination of 2 clubs from a set of 13 clubs. Similarly, we'll let E2 be the event that 2 diamonds are selected. And N2 will be the number of ways that 2 diamonds can be selected. Again, order doesn't matter, so this is a combination of 2 diamonds selected from a set of 13 diamonds. We'll let E3 be the event that we draw 1 heart, and N3 is the number of ways that we can draw 1 heart, a combination of 1 heart drawn from a set of 13 hearts, and that's just going to turn out to be 13. How many different ways can we draw 1 heart from a set of 13 hearts? 13 ways. We either draw the deuce, the 3, the 4, the 5, the 6, the 7, the 8, the 9, the 10, the jack, the queen, the king, the ace. 13 ways. E4, that'll be the event that we draw 1 spade. And the number of ways that we can draw 1 spade is a combination of 1 card selected from a set of 13. Okay? Fundamental counting principle. If E1 can happen N1 ways, E2 can happen N2 ways, E3 can happen N3 ways, and E4 can happen N4 ways, then E1 and E2 and E3, whoops, and E3 and E4 can happen N1 times N2 times N3 times N4 ways, and that would be this many. It would be the product of those things. Now, what about the probability of these four things happening? The probability of 2 clubs, 2 diamonds, 1 heart, 1 spade. Probability of E1 and E2 and E3 and E4, that's the number of outcomes resulting in E1, E2, E3, and E4, divided by total number of outcomes. And that's going to give us, holy moly, this many. Oops. The number of outcomes resulting in E1 and E2 and E3 and E4, that's just N1 times N2 times N3 times N4, all over total number of outcomes. And we're selecting a combination of 4 cards from a set of 52 cards. And if we crank that baby out, holy moly, I don't know what we get. That's approximately the probability of drawing 2 clubs, 2 diamonds, 1 heart, and 1 spade.